of a particular spot. What we're effectively doing is simulating the light coming from a room environment, hitting the spot and bouncing off and hitting the eye. And so the two aspects of this are simulation of the lighting environment itself, how much light comes from all possible different directions to hit this one spot. And the other aspect of it is simulating how is reflect light. That is, here's how much light is hitting the spot, how much of it's actually going to bounce off in the direction that the eye is looking in. So in general, the thing we'll talk about today is the second of those two, that is simulation of various physical type surfaces and how they reflect light to the eye. And this is generally some function of these three vector directions up here on the slide. The vector n represents the normal to the surface, or the perpendicular to the surface at the spot in question. We're assuming that this spot right here is the pixel is what shows through the pixel. So this kind of rectangular region here is some surface. And so at that particular pixel, the normal to the surface is n. The vector to the light source is L, and the vector to the eye is E. And so the functions that we're going to be dealing with will be some functions of those three vector directions. The simplest sort of light reflection model is called Lambert's law, and that's meant to simulate diffuse surfaces. Before we get to Lambert's law, let me mention this one thing. Strictly speaking, light reflecting off of objects, a perfectly smooth object, gives you in effect something like this. It's a mirror reflection thing. That is, light bounces off a surface just like a ping pong ball bounces off a table. And if you imagine this vector here is where the light's coming in, this is the normal vector. A light ray is going to bounce in and it's going to bounce off in this direction. And this blob here represents the direction that the light is going to be bouncing in. Now, if we were to use this light reflection model to simulate something, that means you would only see light reflected to you if the eye happened to be looking in exactly this direction. If your eye is looking over like this, all the light's bouncing off over there, and you don't see any light from this surface. So that means for some multifaceted object that's rotating around, only one or two polygons would kind of gleam at you as they went through just this one direction, and all the rest of them would be dead black. And it's sort of a boring picture, but it would look very shiny because that's what we're modeling, a perfectly shiny object. Now, real objects tend not to reflect light so much. They're completely in the opposite extreme of how light reflects off. It's called diffuse reflection, and that is the surface is assumed to be rough, and the light comes in from a particular direction, and it's absorbed and kind of bounced around with the surface, and the net result of everything is that the light is reflected in pretty much equal amounts in all directions. So here's the light ray coming in. The sphere then kind of represents a plot of how much light is reflected in what direction. If you imagine picking the direction of the eye is connected from the center out here to where the eye is, where that intersects the sphere, that's how much light gets reflected in that direction. Now, one might think initially that this would be a perfectly bland picture as well because all polygons would be equal in intensity. But that's not quite the case. Lambert's law winds up giving us a fairly simple reflection model that works something like this. You have some surface here where the light is hitting. You have a beam of light coming in like this. So that L there is the vector that the light is coming in. And it hits some particular area on the surface. This direction here, N, is the normal to the surface. Now, you can imagine if the light came in at a steeper angle, like this, the area that it would cover would be much more spread out. And if it came in perpendicular, the area where it would cover would be more or less circular. So the total amount of light energy, the per unit area that the thing gets, is a function of the angle that you see here. And the more edge on the angle, the more certain light is spread out, so the less light you've got coming off per unit area, so the less light that you see reflected. And it's not too startling to come to the conclusion that the amount of light per unit area is proportional to the cosine of this angle between n and L. How do we conveniently compute the cosine of the angle? That's just the dot product of n and L. So the Lambert reflection law basically says that the amount of light that you will see reflected is proportional to the dot product of N and L.
L includes the intensity?
Well, I say proportional to, and so there's a, proportionality constants that you can play around with here. Now there's a few things that you have to keep track of in this respect. One of them is the fact that
what happens with the L vector and vector are perpendicular?
well, that's just what I was going to say. If you imagine a top view here, and let's say a top view of, say, a cylinder. So here's the cylinder, and here's the light coming in from this direction, and here's the eye looking in that direction. This particular part of the cylinder, we have to first define a few sign terms. The vector L is the vector from the object to the light. Otherwise, we're going to get a problem here. For this particular spot on the cylinder, N dot L is going to equal to 1 because it's pointing straight parallel to each other. For this part of the cylinder, N dot L is going to be equal to something a little bit less than 1, so it's a little bit dimmer here. For roughly this part of the cylinder, N dot L is going to be equal to 0 because they're perpendicular. So the part that the eye sees is going to be maximum here, and it's going to fall off, get less and less, and wind up being effectively 0 here. For this part of the cylinder, you can still see that part, right? But N dot L in that case is going to be negative because they point in opposite directions. And what that really means is that that part of the cylinder is in shadow with respect to the light source. And that side of it is not getting any light at all. And it kind of makes sense. You imagine all the light kind of coming in roughly this direction here. All this part over here is going to be dead black. So the Lambert reflection law really has a little more complication in that if it comes up with a negative number, that means that you just set it to 0 because that's when we're in shadow. So the next more complete description of it is that. Now there's one other sign convention that you have to worry about, and that is the direction that the normal vector is pointing in. Again, if we take a look at our cylinder from the top view, and here's the vector to the light source. This point here, you can compute the normal vector to it in one of two ways. You can either say it's that, or you can say it's that. Both of those are perpendicular to the surface. And one of them gives you a value of 0, and the other one gives you a value of 1. Which one do you pick? Well, you have to make it so that the vector to the eye, the normal vector points in roughly the same direction as the vector to the eye. That's the convention that makes this work out. And so that means that n dot e is going to be greater than 0. And if by whatever means you've used to compute n dot e comes out with a negative value, then you just flip the sign of n. Now generally for whatever means that you'll use to calculate normal vectors, this decision can be made once per object. If you're using a sphere or a polygon, something like that, the mechanism for calculating the normal vector is going to come up with the same number for the whole polygon, and so you just need to flip the sign once. This is often comes out with the mechanism that you use to define polygons. If you imagine a polygonal object like a cube or whatever, this is defined, the faces of this are defined by an ordered set of vertices, and generally you adopt a convention that the vertices have to be given to the program in some order, for example, in a clockwise order, as you look at them going around the surface from the outside of the object. And This will be clockwise, and this will be clockwise. The clockwise or counterclockwise ordering convention is, again, not well established one way or the other, just like the rotation, positive rotation angles. So you just need to figure out whichever convention you're using, and when you compute the normal vector as a result of this thing, they'll either all point into the inside of the object or all out from the outside of the object. And you make a picture once. If it looks wrong, you flip the sign in your program. You know, the classical real way to do things here. So this gives us a simple method for calculating an intensity for each object. You have to have just a way of calculating the normal vector to the surface. Now, one other thing that we should mention that's a typical approximation that's made, but it's not crucial to any of this thing, is exactly which direction the L and the E are. If you, again, look at, say, at a top view of a cylinder or a cube, something like that, and say that spot right there is the spot that we're interested in. That's what falls in the center of the pixel. What I've been saying so far is that there's one direction L for the light source that we're sort of using for all the pixels. Well, that's really true only if the light source is effectively infinitely far away. If it happens that the light source is sitting right here, it's you know, at a particular XYZ coordinate in the room with us, then the vector from the object to the light source is going to change. The L vector is going to change depending on which spot on the object we are calculating things for. Now this means that it's not inherently more difficult to calculate, but it means that it's more arithmetic. It means for each pixel on the screen, you have to find the location of the spot on the object, subtract that off from the location of the light on the object, and that'll get you the vector direction. Generally you have to normalize these things. The L vector is assumed to be unit length, incidentally. And so once you subtract off these 2 points, then you have to renormalize that thing, which involves taking a square root and dividing into all the components. Then you have a unit L vector for that particular point. If you're using a local light source, then you have to do that for every pixel on the screen, because every pixel on the screen is going to have a different light direction vector. Likewise for the direction to the eye. We assume that the eye is down here. Now, so far in the Lambert's law, the actual vector to the eye doesn't matter. So, haven't worried about it too much, but in later models, the vector to the eye will matter, and so you also need to subtract off for each spot on there if you're using local eyeball locations. Now, really, for a lot of useful pictures, you can assume the light source is infinity, and you can assume the vector of the eye is constant all the way across, and you'll get reasonable looking pictures. But for interesting, more realistic and more artistic sort of effects, you have to subtract off. I think there was a question back here someplace. Okay.
Are there incremental methods to do that, so you don't have to recalculate the normalizing?
Incremental methods to calculate a new light vector direction would probably only be approximate, because of the fact that you have to have a unit length vector, which means that there's going to be a square root in there, and if you kind of look at how the value of the light direction changes as you go across, it's some second order curve, and you wind up having to, in order to do it right, you have to do a square root somehow. Now notice that this thing means that even for a planar object, if we have just a flat surface here and a local light source like that, and we're viewing it from down here, and the eye is down on the bottom someplace. These are all top views now. Even for a perfectly planar object, the intensity across that plane is not going to be a constant, because each spot is going to have a different vector to the light source. But again, the common approximation that's made is that the vector of the light source is a constant, and so for planar objects, simple algorithms will take all the facets of the object, and each facet will have a constant intensity going all the way across it. And so you're shading in polygonal shapes on the screen where the polygonal shape has a constant intensity. Here is an example of such a thing. Let's have a couple of simple objects here just to show what it looks like. Cube this sort of from the top in the upper right-hand side. This face back here is basically black because the light's coming from the opposite side. The normal vector points away from the light. Here's a, pardon me?
Go back to that.
Yeah.
Is that the best anti-aliasing that can be done?
This is no anti-aliasing at all.
One more thing about that last picture. Is it an illusion, or is it the intermediate planes are getting darker at the edge there, at the top edge?
This here?
No, the front one, this one here.
Yeah.
It seems to be radiating from the top all the way down.
It certainly wasn't calculated that way. There are several things that can be that. We're going to talk a little bit about optical illusions in metal and in a minute. So it could be because of that, and also could be because the screen is a little bit darker up here than the top. You know, there are an awful lot of bizarre things that go into crap up your picture for you. It's incredible. Another simple object is a sphere. I use a sphere a lot as a test object for normal vector calculations and lighting models because it's simple to calculate and because it gives you kind of all possible normal vector directions. Someplace on the sphere, the normals are going in all different directions, and so it's good for giving you a global idea of what's going on. Here the light's coming in from the right-hand side, and you see kind of the maximum intensity right about there someplace, and it trails off to zero. So this is kind of the day-night terminator over here. Now there's one other thing that's typically done with this that is a sort of elaboration of the lighting model, and this is takes account of the fact that even though on the one side of the sphere you expect it to be dead black because there's no light shining on it, if you do that, it looks like parts of the object are disappearing. People are always asking you what happened to the back of the handle on the teacup and stuff like that. So generally you don't set the thing to dead zero. You wind up including one other term in the lighting model, which is commonly called ambient light. And that's just a constant bias that you add into the intensity of everything. The idea being that there's some light kind of coming from all directions of the room, bouncing off the walls and so forth. And so even things that are facing away from the single light source are getting a little bit of light from some other direction, potentially. So the total light reflection, or the intensity that you see on the screen, is going to be some value, a proportionality constant for the ambient light, and proportionality constant for the diffuse reflection, or the Lambert reflection. So you have the sum being something like that. Now PA and PD are just two numbers that you pick more or less for aesthetic purposes. A lot of the models that we'll have here have certain free variables that change the character of how the light works. And we generally don't simulate real surfaces accurately enough to say, well, for wood, PA is going to be 0.003, 0.75, and so forth. You just plug in different numbers until they look good. And generally I use a PA value of something like 0.1 to 0.05, someplace in that neighborhood. And PD then would be 0.9 to 0.95. Good numbers to start with. Generally we want to keep PA and PD so that the sum is equal to 1. Otherwise, or at least less than 1, less than or equal to 1. Otherwise, you're going to be in trouble if max of n dot L equals 1, and these two things add up to something greater than 1. You're going to have an intensity that overflows the screen. Now, PD might be less than 1, or less, less than 0.9 or something like that. PD you can think of sort of as the color of the object. The albedo, as it's called in some places. What color gray paint that you put on the thing. So you can have it 0.5 if you want to. So the maximum brightness of the thing is going to be is 0.5 even directly under the light. And you have different objects have different values of PD on them. So PD is sort of the color of the paint. Strictly speaking, if you scale down PD by a certain amount, you probably will scale down PA by a certain amount if you're thinking of that as ambient light coming in from bouncing off the thing. paint's going to absorb the same proportional amount of ambient light as it is from the direct light.
You're going to go into color models more directly later?
Yeah, I don't want to elaborate on color models too much right now, although I'll have to mention a few things about them because L.B. Smith is going to talk about color models a little bit next time when he talks about painting algorithms.
Usually model these surfaces real accurately, that it's like wood, different materials have different parameters. Are databases of any sort beginning to appear with numbers like that?
Databases exist, although typically they're only just beginning to be used. The models that are being used are not quite that accurate anyway. One of the things that's interesting to know is, the eye is used to seeing things, and it likes to make sense out of anything it sees. And you can use the most bizarre crapola functions you can come up with that make no physical sense whatsoever, and they'll look like something. You can always come up with some surface that reflects light like that. If you look like velvet reflects light in an extremely bizarre way, because if you imagine a cylinder made out of velvet, it looks brighter on the edges where the light's coming in perpendicular to the surface than it does in the middle, right? Because that's where all the hairs are sticking out and the light's bouncing off the hairs. So there's a lot of room for experimentation with bizarre lighting models in order to come up with different effects.
So generally you just have this interaction with the image displayer?
Yeah, there's a lot of artistic involvement that you can do right here. A couple of little random pictures here. The idea here is, diffuse lighting models. They tend to make things look sort of like chalk or felt, very matte surface type things. And now here we have two matte surface things, the yellow and the orange. Sorry, the teapot and the teacup, for those of you who are watching in black and white. The other things have highlights on them, which is what we're going to get to in a bit, which is a much more interesting sort of surface reflection function.
Are the models of these objects stored as curved surfaces or what?
These are, right, which is what I want to get to right now, curved surfaces. So far we've just talked about flat polygonal models of things, which are the easiest to deal with mathematically, so that's why they were historically started out that way. Now, if we want to make a picture of something that's a curved surface, one of the simple ways of doing that is to model it as a whole bunch of polygons. So here's a potentially curved surface with a few polygons on it. Now we can see that this, you can get a general idea that it's some sort of surface revolution, but it doesn't look real good as a smooth surface, right? You can see obviously each polygonal facet here has one constant intensity across it. So the general thing, first thing let's try, of course, is to use more and more polygons. And as you use more and more polygons, you get closer and closer to the shape of the real surface. But as it happens, things don't look smoother until you wind up almost with one polygon per pixel on the screen. And the reason for this is a result of several things. One of them is the fact that what we're really doing is we're approximating a function here. In general, computer graphics is a big approximation game, is that it's almost always too complicated or too expensive to do it right, so you have to come up with some good approximation to it. If you look at the perfectly smooth goblet that you would like to draw here, and kind of imagine one scan line going across this thing, the intensity along that scan line, if we plotted it along here, here's the x direction and here's the intensity axis, we black down here until we got to the surface, and it would suddenly jump up and do some smooth curve and go down to some other value and jump down to black again, right? So this is the ideal intensity profile that we would like. Now if we divide this cup up into a lot of polygonal facets, like that, and color each polygon in at a uniform intensity, that means going across this polygon, we're going to use some constant intensity there. So what we're doing is we're approximating this curve by a bunch of stair steps, effectively, of equal intensity values. which sort of approximates the general shape of the curve there, but a bunch of constant stretches like that is not a particularly good approximation to a curve. What we would really like to do is to approximate it at least by a piecewise linear sort of thing. So you pick a bunch of points along the curve. I'm making another diagram here. Here's what we'd like. And so we pick a few points along the curve and we calculate what their intensities are, and then we do some linear interpolation in between them of intensity. This particular interpolation trick was first done by a guy named Henry Goro at the University of Utah, and so it's typically called Goro Shading, although I prefer to call it Goro Interpolation because you're really interpolating intensities between places. The term shading implies something slightly different, at least to me. What it means is that when you model an object as a bunch of polygonal facets, if that object is supposed to really represent a curved surface, what you should do is include it in your model for each vertex there. Instead of just the x, y, z coordinates of the point in space, you need extra information. You need the surface normal vector to the surface at that point, whatever that might be. Now, for simpler modeling things which generate surfaces of revolution, you can calculate normal vectors directly from the mathematical definition of the thing when you're chopping it up into polygons, so you can include those in along the way. If you happen to have just a mesh of polygons that are given to you that kind of form the scheme of some arbitrarily curved objects, you need to somehow generate approximately what the normal vector probably should have been at that vertex. Typically what's done in that situation is for a corner here between four polygons, like right there, it would take the normal vector to each of the four polygons and average them together, say, to give you a normal vector that represents the direction that the normal is pointing at that vertex. And you can start playing other games too. You can say, well, suppose these polygons happen to be radically different sizes. Let's take a weighted average of the normal vectors, weighted by the area of the polygon, and various other mathematical witchcraft on that. It starts becoming a little bit subjective at that point. But once you have a normal vector for each vertex on the polygonal mesh, then when you go to shade in the polygon rendering, you calculate intensities not for the normal vectors of the facet, but you calculate the intensities from the normal vector of the vertices. So now you have, at each vertex, you have the x and y location on the screen, and you have the intensity value. So that when you go through to scan a polygon, using a large polygon here on the screen, I1, I2, I3, and I4, there's an intensity for each vertex there. As you scan across in a particular scan line, you need to do an interpolation of the intensity values between the four corners. The way that's typically done is to first interpolate intensity values along each edge. So for this edge here, the intensity is going to linearly go from I1 to I2 as you go along the edge. For this edge down here, the intensity is going to linearly go from I1 to I4 as you go down that edge. And so since we're kind of halfway down this edge at this point, the intensity value here would be I1 plus I2 over 2. And since we're about say the fifth of the way down here, the intensity there would be like 0.2 I1, that's going to be a bit small, 0.2 I1 plus 0.8 I4.
I think that's actually backwards, isn't it? Don't you want it to be really close to I1?
Backwards, right. So as you go down here, the thing goes from I1 to I4 linearly. Now, linear interpolation is fairly easy to do, and it's also fairly easy to do incrementally. Since we're going to be possibly doing some interpolation of other things as well as intensity, like Z information, we can kind of include all these auxiliary pieces of data into kind of a common structure for each vertex and each edge that we're keeping track of as we go along. And when you initially start out calculating the intensity, for this edge here, when it starts becoming visible on the first scan line, you figure out the distance between I1 and I2. That's the change in I going all the way down the intensity. And you figure out the change in vertical position on there, which is the delta y. And so you store just an incremental value here of delta I over delta y. I don't know what we'll call this thing, but this is just the change that we're going to have in the intensity per scan line. So you have a kind of a register within your program that keeps track of the current intensity going down here. Each time you drop down one scan line, you just add this value into it. And this happens similarly to the z's as well. So one of the nice things about this algorithm when it was first invented is that it used exactly the same mechanism for interpolating intensities as already had to be done in order to interpolate the z, the depth information. And it makes it easy to add into hardware as well. And so most of the hardware curved surface style real-time simulation systems use this Goro shading trick in order to make smooth surfaces instead of these lumpy polygonal things. Mach bands, right. Glad you said Mach bands. Now, the first reason that just lots of little polygons doesn't work too well is the fact that, as I said before, we're approximating a perfectly smooth function with a bunch of little stair steps. Now, that in itself is not awful. It might not be too accurate, but it turns out that the way the eye works, that it makes it even worse than mathematically it would be. The way the eye interprets pictures, an intensity profile of, say, one scan line, like that, and had a profile like that, which was basically kind of a medium gray area, then a sharp transition to a very bright area, then a sharp transition to a less bright area. Turns out that the way the eye responds to that is not exactly in this fashion. It responds, there are various models of exactly how this works, but every time the intensity transitions, the eye kind of accentuates the transition. There's your picture. That is where the thing suddenly jumps up, the eye kind of exaggerates the jump a little bit. When the thing suddenly jumps down, the eye kind of exaggerates the jump down a little bit. So that when you have a boundary between two different intensities, the thing looks a little bit brighter on the left side of the boundary than it really should, and looks a little bit darker on the other side of the boundary than it should. Now, this can be variously thought of, so the eye is sort of performing derivative functions. This is sort of has some components of the derivative of the picture in here. Or you can also think of it as the eye as a high-pass spatial filter, if that makes sense. We're going to get into spatial filtering of images when we get into aliasing. Basically means that sharp edges are exaggerated and general slower undulations are de-emphasized in the eye. Now, this is going to happen to any sort of intensity profile that you get here. And in addition, it's going to happen even if you're using a linear approximation to the surface. So just the Goro shading itself is not going to solve all of our problems. If we have an intensity profile that goes like this, the eye is going to sort of make little lumps here at the transitions. Yeah.
Shouldn't it be possible to stick into the Goro shadings some kind of correction for that?
It would be possible to stick in some correction for that, yeah, except that the amount that this happens for different people is different, and it depends on how much light is shining on the object and things like that. If you try to really outsmart the system, you can kind of get into trouble that way.
So it's very subjective?
Yeah.
But have there been any attempts to do it just to see what it looks like?
I can't think of any that have been attempts to do that specific thing. I've heard of attempts to exaggerate it for the image processing point of view. If you have an image that somebody hands you that's kind of dull and flat and washed out and bland looking, you run that through a high-pass filter and that exaggerates the edges and makes the thing a lot crisper. but that's kind of the reverse of what you want. Might be an interesting project to try, kind of filing off the edges like this. But even with Goro shading, where you have these things here, you get these little lumps in here. Now the lumps here were first discovered or talked about by somebody named Ernst Mach, and so they're typically called Mach bands. And if all goes well, we might have an example of one here. This particular picture has a linear intensity profile. That is, over here it's dead black. Over here it was supposed to be total white, although the picture's a bit underexposed. And this band here in between is a linear ramp between dead black and dead white. Now, how many of you people can see what looks like a bright stripe going up and down here? You all pass. Good. That's the Mach band. It's not really there. The intensity profile of that particular picture is exactly what I drew on the left here on the piece of paper. Goes black, straight line, white. That thing right there does not have a lump on it. It goes just straight up to white and stops.
So you can't see them on television?
Quite possibly so. The television also has little bandpass filtering gadgets in there. If you file it off at all, you can get this. This picture originally came from a television monitor, but it was a somewhat higher resolution one probably than we have here. Now, the question of Mach bands brings up the general category of optical illusions. One of the kind of interesting things, at least to keep in the back of your mind, is a little bit about how the eye works when you're making pictures, because it can help you debug programs, because sometimes it turns out that things that look wrong on the screen are really right, but it's just the eye that's fooling you a little bit. One of the other classic optical illusions is called simultaneous contrast. The question is, which of these two gray squares is brighter? How many people think this one's brighter? How many people think it looks brighter? Good, good. How many people think this looks darker? Great. Well, of course, they're the same brightness, and it has to do with the contrast. That is, a medium gray looks brighter against a black background than it looks against a white background. Another thing also is this thing looks brighter on this side than that. There's no particular reason for that, so it's probably more a matter of the fall off of the TV screen when the slide was made rather than anything else. Also, there's other lights kind of shining on the screen.
It might also have something to do with projectable, too.
Yeah. It's kind of the same situation in early physics, you know, when you're talking, people were talking about, Aristotle was talking about feathers obviously fall less fast than stones. You know, you have to be able to extract out just the features before you can make any generalizations. Yeah.
Wouldn't you expect to get Mach bands at the edge of the boxes?
Here, you'd expect to get perhaps some sort of Mach bands, but they would be kind of the same going in this direction as in this direction. That is, this looks a little brighter here than it does in the middle, but this should look a little brighter here than it does in the middle as well. And it doesn't, at least from where I'm sitting, but partly it's because the monitor was not quite in registration here. You can see a little bit of color fringe there. So, with Goro shading then, we can improve things, but you can still see Mach bands. Here's an example of a picture which should show it fairly noticeably. This is all done with Goro shading. It's a model of a brain. It was reconstructed by a bunch of cross-sections of the brain that were digitized, and then polygons were fitted in between it. There are not an awful lot of polygons fitting across the surface, but you can see kind of light stripes here, which are really the edges of the polygons. There's really maybe only 3 or 4 polygons going across one little convolution of the brain here. So if you want to improve on Goro interpolation, basically what you have to do is come up with a smoother function to approximate the real smooth function. The next improvement on that was done by a guy named Fong at University of Utah. And he said that rather than calculating an intensity at each vertex and interpolating those, let's just keep the whole normal vector around. all three components of it, so that as we're scanning across one scan line, you interpolate each of the three components of the normal vector as totally independent numbers here. And so the x and the y and the z components of the normal vectors are each separately interpolated as you go across this, as you go down the edge and across the scan line, so that you'll have a different normal vector for each point on the surface. Now what this means is not only do you have to interpolate the components, but you have to rescale it to be unit length for each pixel on the screen. Otherwise, if you plug it all into the algebra, it turns out if you don't rescale it each pixel, the effects cancel each other out, and you get the same thing as you would with Goro shading. So you interpolate each component of the normal vector along here, and so for each spot on the screen you have a whole different normal vector. And in a sense, what you're doing is trying to reconstruct some sort of curved surface that interpolates the edges of the object. And for that, you get a pretty good picture, because it's a real smooth intensity function. It's really curved, and it changes from one pixel to the next. Now, of course, the real solution to this thing is to really solve the equations that it would take to represent curved surfaces directly, rather than hacking it up into a whole bunch of little flat polygons. Higher order surfaces are what we're going to get to next time, but we'll leave this at for the time being, yeah.
Now, all these techniques, if you saw the edges of the objects, you'd see straight edges. Even
That's right, yeah. The Goro interpolation and the Phong interpolation only make the inside of it look curved, and you can still see certainly straight edges on the outside edge. That turns out to be maybe not as objectionable as you might think, because certain cases the eye is easy to fool into thinking it's seeing a curved thing. I mean, you can see that they're straight edges, but they don't seem to bother you as much as you would expect them to.
And you'd also see, when you saw a polygon almost on edge, it would look flat even though it was supposed to be curved. I mean, you're seeing a part of the polygon that's supposed to be hidden.
That's an interesting question. The polygons that are almost edge-on present sort of a problem in this Goro and Phong interpolation in the following sense. Let's again take a top view of cylinder here. Here's the eye looking at it. Make sure I get the vectors going the right way. The eye is down here someplace, kind of looking up at it. Let me specify an actual eye point here. Now this is all going to be done in what I would call real space. This is before the perspective transformation, and so all of the intensity calculations have to be done in this real space without any unequal scales applied to x and y, and without any perspective transformation done, because that's normal vectors and dot products all have to be done in that space. So in that sense, if we take the tangent to the cylinder from the eye point, these two locations here are going to be the silhouette edges of the cylinder. Those are the edges of what we're going to see. Now, after it goes through perspective transformation, this circular cross-section of the cylinder is going to turn into some bizarre elliptical shaped thing, but for the time being, we're all doing it in real undistorted space here. Now, if we were to approximate the cylinder with a bunch of little polygons, let me be careful and draw this diagram so it illustrates what I want to show here. Say 8 polygons. And we have the eye sitting down here like that. And where it's tangent to these polygons, it's going to see something like this. This doesn't quite do it. I want to... trying to reconstruct the geometric situation that illustrates the problem here. Something like that. Here's the eye. The idea is we're going to see this polygon here, and we're going to see a little slice of this polygon here. This polygon here is going to give us some trouble, because the normal vector like that points towards the eye on that side. And the normal vector here, since it's sort of around the corner from the real silhouette outline, points away from the eye. And that means that if we had the program be real dumb and just say, here's a normal vector, the n dot e is less than 0, so that means we have to flip the sign of the normal vector and use that normal instead. You're going to get an intensity calculated for this point that would have been what you would see kind of on the inside of the cylinder if the front half was missing, which is not what you want. Really, this thing points away from the eye, and so you have to have the program have a little more high-order knowledge of the structure of the object rather than just the normal vector at this point. You have to have the direction of the normal vector picked based on which polygon it's on. And in this case, actually, the intensity of this thing is the intensity of a point that you wouldn't be seeing. It's going around the corner, and so you generally need to interpolate it into the intensity that would have been for the real silhouette edge or something like that.
Even then, depending on how crude your polygons are, the sides of the cylinder as it rotates are going to get smaller and wider.
Right. It's an approximation. It's cheap, but it doesn't. It certainly has problems with it. There's one other problem with Goro shading as well, which a lot of people stumble across and run into problems. Suppose we have a polygon something like this, concave polygon. And suppose the intensity, for whatever reason, I'm going to exaggerate this. Now, the intensity of each of the vertices is like that. Typically, it wouldn't be quite so distorted, but as we scan across this thing, the intensity of both vertices is 1, so the intensity all the way across this thing is 1. As soon as we hit down here, however, we're scanning in an intensity going from 1 down to 0 here, and from 0 up to 1. 1 down to 0 and 0 up to 1. So you're going to get a kind of dark edge going through right there. It's going to be totally white up here on the top, and as soon as this extra vertex shows up, you're going to get the thing going from white down to black and black up to white again. And as you rotate the polygon on the screen, the place where that funny edge happens is going to stay horizontal. Very unpleasant. Basically, it means that Goro shading doesn't work too red hot for concave polygons. You better keep your polygons convex. Oh, tape change, yes. Time out for a word.
A lot of machines nowadays give you pretty much hardware square root for free along with the rest of the floating points. About as simple as a divide. Some of the stuff I've fiddled with these, I found a lot of times you could have these immense lookup tables that, considering machine memory sizes nowadays are not all that immense.
Right.
They give you stuff you could interpolate through without doing the square roots or normals or anything.
As long as you have a good idea what the ranges of the values are going to be, then right. Now, if somebody just hands you a vector on a platter and says normalize this thing, you might be in trouble because you have no idea what the maximum range of that vector might be. If the normal vector is being calculated by mathematical transformation of the equation that defines the surface, different size surfaces are going to give you a fairly wide range of possible normal vectors. Yeah.
It seems to me that the shading here would fail even on a square that has three corners at intensity 1 and 1 at intensity 0.
Yeah, it's going to give you slightly bizarre results for even that.
So even having all
the thing is, well, it's not going to be quite so bad in that you're going to get what's called bilinear interpolation between these values, which is going to give you at least the same intensity independent of rotations of the squares. I believe it works out that way.
not inside the square. It's like if the 0 is at the bottom and the whole top half of the, like that, then the whole top half of it would be at intensity 1 until we started interpolating the bottom 2 lines.
Well, when we go across like this, we're all at intensity 1. If we go across like this, it's intensity less than 1. Yeah, you're right. It's not going to be the same. Works best for triangles. Don't use Goro shading. Use higher order equations, and life will be happy. I hardly ever do this too much for things other than very simple shaped objects, flat surfaces, or things that are cylinders, things like that. So that's simple diffuse sort of shading, the next thing we want to talk about a little bit is highlights, which involves a little more fancy modeling of the light reflection properties of the object. So far we've sort of talked about the two extremes of the spectrum. We've talked about a perfectly shiny object which reflects light only in the mirror reflection direction, which never happens in real life and be kind of boring to simulate. And we've talked about a perfectly diffuse object which scatters light equally in all directions. A specular object, or an object with highlights, is someplace in the middle. And this is kind of a plot of what it might do. Have the light coming in from the upper right here. This vertical line here is the normal vector to the surface. A little round circle there, if you can see it, is a tick mark at unit length. But then there's this hemispherical component here, which is the Lambert's or the diffuse component of the thing. But it is reflecting a little bit more light along this direction than it is everywhere else. So this is someplace between perfectly shiny and perfectly diffuse. And what it winds up being is that you have the net reflection function is a sum of two components. One is the diffuse component, which is just n dot L. And the other one is called the specular component, which is highlights, which we'll investigate how to calculate that. And that's this lump that's sitting on top of here. And as a matter of fact, as an example of a picture made with that, this particular picture was made with that same light reflection function. And you can see the bright highlights here and here. And highlights are good in that they tend to help out defining the shape of a curved surface object. Now we have a little bit of recursion problems here in that this particular function was defined in the computer this plot was defined in the computer as a shape. The actual light that's lighting this model is kind of coming in from behind us and on the right here. And so this is the lighting model is used to light a shape which was independent of where the light was on the shape. Okay, how do we calculate how much highlights are? Here's our surface that we're interested in. Here's the vector normal to the surface, and here's the light coming in, the direction that the light's coming from. All these vectors are from the object to the light, or to the normal, or to the eye, just to get the sign convention set up. Let's define another vector over here, which we'll call R. R is going to be the direction that the light would bounce off in if it was equal angles of incidence and reflection. How do we calculate R? What's R in terms of N and L? N and L are going to be given to us. R equals what? Well, it's calculated by doing a little bit of dot and cross product style things here. Let's take a look at just this component of N here. We're going to separate the L vector into two components. One is perpendicular to N and one is parallel to N. The perpendicular component here is going to be N times L dot N. All these vectors are unit length. And so the projection of L onto N is going to be in the direction of N, so that's the vector N here, and it's just scaled down by this number L dot N. The perpendicular component of L is going to be just L minus this. If the horizontal component plus the vertical component equals L, then the horizontal component equals L minus N times L dot N. Put arrows over the vectors so we can keep track of what they are. So what's R going to be? R is going to be the same thing except this perpendicular component points in the other direction. So it's going to be minus the horizontal component plus the vertical component. So R equals minus L minus N times L dot N plus N times L dot N, right? And you munch around with that a little bit and you can come up with 2N times L dot N minus L. So that's the vector that all the light is going to bounce in. Now, if we assume that this thing is more or less a specular thing, but it's not a spike coming out here exactly, but it's kind of a bump trails off a little bit. So if you're exactly looking along that direction, if the eye is exactly parallel to R, you're going to get the maximum amount of specular component. If it's a little bit away from R, you're going to get a little bit less. If it's a lot away from R, you're going to get a lot less. So basically, the amount of specular light that you're going to see is the angle between the eye and R here. So it's some function of I dot R. That function we expect to look something like this. Be careful a little bit how I define it. It's going to be sort of bump shaped like this, and it's going to trail off as you get farther and farther away. Now this angle axis here is the angle between E and R. So when the angle is 0, if they're parallel to each other, that's here, and it's a maximum value. Let's label this axis S. Specular amount is like that. E dot R in that case is going to be equal to 1, actually. And so as E dot R is equal to 1, then we're at this point here. When E dot R starts getting closer and closer to 0, that means the angle between the two is getting more and more equal to 90 degrees, and it moves up here and falls off. Now the function that Fong happened to use for this thing was E dot R to some power. And when E dot R is equal to 1, then the thing is equal to 1. And if you raise it to a power, basically, the higher the power, the sharper the fall off, the bumpier, the spikier this thing is. He just picked this function out of a hat because it happened to have roughly the right shape that he wanted. It seems to have latched on to a lot of people, and they keep talking about the highlight power or the specular power, which is just this value P here now is one of these free aesthetically adjusted variables for the sharpness of the highlight. And it's not necessarily related to any physical properties of the surface other than intuitively, really. Now, we now have a net intensity that's the sum of three things. A proportional amount of ambient light plus a proportional amount of diffuse light times the diffuse function, maximum of 0 and n dot L, plus the proportional amount of specular light times E dot R to some power. And so we now have these things here. These four numbers here are essentially properties of the surface. We can kind of shuffle them off in that direction and say that they are to be adjusted based on aesthetic grounds. Typical numbers that I use for this, 0.05, say, P, D, 0.7, PS, 2.5. The power on here, you usually have to use a surprisingly large number in order for it to do reasonable things, like 60, which sounds like it makes something enormously spiky, but it's not nearly as spiky as one would think. Now, a function that I have used with at least some vague physical justification is a little bit different from that. I'll look it up here, because I don't remember it off the top of my head. Okay, let's sort of bizarre thing. It's got a free variable in there which we'll call k. K squared over this big mess, E dot R squared times quantity k squared minus 1 plus 1, and that whole mess squared. This was extracted out of some paper on how surfaces are modeled in a certain way, and there's some justification for it. The punchline here, however, is that this has roughly the same shape, basically. It's a bump in the middle, and it trails off at the edges. And this value k here adjusts the spikiness of the bump to make it either spiky or real spread out for real sharp highlights or real spread out highlights. However, this function here is somewhat easier to calculate than the e dot r to the power. E dot r to the power, in order to do that, you have to take a logarithm and multiply it by 60 and take the anti-logarithm and all these things. And this really turns out to be just a couple of divides. And since k here is a constant, this whole thing and this whole thing you can calculate outside of the loop and keep those around. So it's just multiply, add, divide, and another multiply. So it's 2 or 3 multiplies and a divide in order to get it here. And this sometimes gives, this has some more physical justifications here.
Okay. As long as you're talking about actual, tricks for computing these things fast, when that p that you chose is 60, do you always want, really exact control over it, or couldn't you always choose it to be a power of 2 such that you could compute it in a couple of multiplies rather than log and so on?
The value of p for thing to the power is, the property of the surface, which probably a factor of 2 wouldn't give you enough resolution to do it as much control as you like. The value of 64 might be okay for one particular object, but you might want to have one that's maybe half that shiny. The only other choice you get is 32, which is not shiny enough, and so you might want a little bit more things in there. Also, quite often for things to the power, you can use some table lookup thing as well to do that.
What's a typical value of k?
Typical value of k. I don't remember off the top of my head, but it's the neighborhood of between 0 and 2. It's that general ballpark. Basically, what's interesting to do is you can represent k in terms of the angle at which this function falls off to half of its maximum value. So if you plug this thing as this is equal to 1/2, for e dot r is equal to square root of 2 over 2, 45 degrees. And then you can solve that for k, and that'll give you a number that would work fairly well. Well, let's take a look at a couple of pictures of what this generates. Here's our friend the sphere, and here's a highlight on the sphere. We did highlight in black and white on the previous picture. Notice on a color picture you make the highlights white. We haven't quite talked about what color does so far, but generally speaking, colors are represented as 3 components, red, green, and blue, for additive color. And so you'll be calculating 3 different numbers. In the case of diffuse reflection, back over here on the equation, we'll have a different value here for PD for each of the 3 components. PD is basically the color of the paint, right? And so there'll be an intensity for red, which is going to be this whole thing with PD red, and intensity for blue, which is the whole thing in here with PD blue, and intensity for green, which is everything in here for PD green. The P specular, however, would be the same for all 3. And the motivation for that is the fact that you come up with, at least to start with, white light, bounces off the surface. The specular light is pretty much the thing's kind of bouncing just off the surface. The light doesn't really interact with the surface or the pigments at all. So all of it gets bounced off. That doesn't get bounced off. It gets absorbed and bounced around, and gets some of the light gets sucked up by the pigments. That's what will be reflected as diffuse reflection. So that the specular component reflects all the colors, whereas the diffuse component scales all the colors by the different components of red, green, and blue of the pigment or the paint that you've got in there. Now, there are various simplifications and cheats in there, and you can get more elaborate than that in terms of how you're modeling the brightness of things. Quite often you want to exaggerate a little bit the whitening of this. And if you have the diffuse component be kind of 3/4 of the total contribution, and the specular component be 1/4, which are the sample values I gave for PD and PS there, this highlight is not going to be quite as white as you'd like. So sometimes you enhance that a little bit. Yeah.
Is that apparent darkening around the specular reflection something akin to a Mach band?
This here?
No, well, just out a bit, it looks like there's a darker purple. I don't know if it's Yeah, right.
Oh, could very well be, yeah. Yeah. Right. I hadn't really noticed that before myself. Yeah, I might even be able to see it better on the monitor. Huh. Okay, what else we got here? Here's a example of a whole bunch of spheres. Sort of shows you how the highlight disappears. This is an array of spheres with light coming at it from 16 different directions. And so it's another test of what the shape of the highlight looks like as the light kind of goes over the horizon. This is a bit highly exposed. You know, these down here are almost the dead night side of it, and what you're seeing here is just the ambient light component being a little bit high in this case. Here's our canonical teapot with bright shiny highlights on that. Everting sphere, on and on. One of the interesting things when we get into texture, and I'll at least briefly notice, is the texture on this thing, the color is changing from one place to the next on the surface, right? Except the highlight part here is not affected by the pigment, and so the highlights tend to wash out the texture a little bit. You can't see the texture pattern underneath the highlight, which is more or less what happens in real life. Now that's the model that Fong used. There's another more elaborate model which I'll briefly describe, which again was done by some physicists. Dug this out of the Journal of the Optical Engineering Society or something like that. I might just mention in general that it's often quite interesting to go rooting around in journals of that nature, Optical Illumination Engineering Society, things like that, because there's a lot of work done by physicists in how light interacts with real surfaces and simple mathematical models for how this works that hasn't really been absorbed by the computer graphics community yet. Many of the lighting models that are used are very simple, and a lot of them don't have a lot of physical justification for it. They just use them because they're easy to calculate, and they make pictures that look more or less believable. But it's possible to find lots of interesting other lighting models. Some of the others that I've discovered, but I haven't even tried out yet, are like this. So it's a good research sort of project. The Torrance Sparrow model modeled effectively the specular reflection as a collection of a certain type of surface. Missed a few slides here. This is one other quick showing of, this is a bunch of bumps on the surface here, again to show that the specular component tends to make the surface relief a little bit more obvious. This is just a diffuse model. That's a specular model. Okay, the Torrance Sparrow thing assumes that the object looks sort of like this in cross-section. This is our rough surface that we're going to be simulating, and it has a whole bunch of flat facets in it that are pointing in sort of random directions. And the whole thing is a statistical model based on the distribution of the random directions that these little flat facets point in. The idea being that if we, again, make a diagram of our surface, and here's the normal vector to it, and here's the direction the light's coming from, and now let's actually include explicitly the vector that the eye is looking from, just kind of pointing out of the paper a little bit towards us. Now for this eye direction and this light direction, if we take the vector that's sort of halfway in between them, we'll define that as being h. That's the vector kind of independent of the orientation of the surface. That vector h is going to be the vector that all the little facets have to be oriented in order for us to see specular reflection off of. Anything with a normal vector pointing along h will see specular reflected towards us. So what they said is, given this normal vector direction, we will assume that there are a statistical distribution of little facets that are pointing not exactly along that normal direction, but at different angles relative to that. And so there's kind of a distribution here a number of little microfacets, shall we say. As a function of the angle between n and h in this case, or n in whatever direction that we're kind of measuring. Most of them are really, parallel to n. And as you get looking for little microfacets that are farther and farther away from pointing direction to n, you get less and less of them. So in this case, we have the specular amount is some function of n dot h here. Now, the function that they used was a little bit more elaborate than Phong used, because they were trying to predict a few other physical properties, in that the whole specular amount was a larger thing. I'll repeat that down here. S equals dgf over n dot e. There are really three terms in this thing, dg and f. The n dot e term is, the explanation for that is the fact that as the thing tips away from you, you're looking at a larger cross-section of the object here. That is, here's the surface, and here's the eye, and n and e. And you're looking over a larger surface area of the object, and so you have to scale up the total number of little microfacets that you would get over that larger area. The d is a distribution function here of number of microfacets going in a particular direction, and so as you get farther and farther away from this h direction, you get less and less of them. Farther and farther away from the normal direction. If h gets farther from the normal direction, you get less of them. The value of f is called the Fernell Reflection Law, and that's some bizarre combination of sines and cosines and tangents, which is derived in electromagnetic theory to describe how light reflects off of surfaces. And the interesting thing there is that it has somewhat different values for metals and nonmetals. Now, it turns out this is purely a function of E dot h, which is a constant for any particular scene. And so this is kind of a global scale factor for the whole thing. But basically, it means that metals will have brighter highlights than nonmetals. And the value of g is something that I couldn't believe would be possible to calculate at first, but it's supposed to represent the fact that once these little microfacets shadow each other. That is, the light that's coming in from this direction like that will get shadowed by this side of the facet, so that only 1 minus m over L of this facet is really going to be hit by the light. And so that's what's called a geometric attenuation factor. And for light that's coming in away from the perpendicular direction, you're going to get more and more attenuation factor as the light gets hit more and more edge on. And there's a formula for calculating this thing, which is in a paper that describes this thing that I won't elaborate on right now. What I want to show, though, is just kind of the result. What it turns out is that this Torrance-Sparrow model gives you almost the same results as Phong's model in most cases. They're close enough so that there's not a major difference. 4 light sources that are shining almost perpendicular to the object. And when the light source starts getting more and more edge on, however, they start getting more different. This is what Phong's model predicts for a light that's kind of edge on. It's coming in at a fairly steep angle here to the normal vector. The radius of the bump here, n dot L, is fairly small then, but the size of the specular bump is a constant here. So Phong's model would predict this. Torrance-Sparrow model predicts something like this. It's got a larger bump here, and also the maximum extent of the bump doesn't happen to be exactly along the mirror reflection direction, which happens to be something that they measured, which is what they came up with this function in order to predict, was that the maximum direction here wasn't exactly along this reflection direction for all these geometric attenuation things get included in. The other interesting thing, however, is that the size of this bump is a lot more. Now, you can experimentally verify this by taking a look, say, at a sheet of paper. As long as you look at the sheet of paper kind of straight on, it looks like sort of matte finished paper. But if you hold the thing up kind of to the edge of the light, so the light's coming in at an angle and bounces off of it, you'll get a highlight on it. So the thing looks more specular the sharper the angle that the light hits it. Here's an example of that. This is for a diffuse object now, so that when the light's coming in from more or less behind us, it looks matte surface. But as the light kind of comes in around the horizon, you get this sharper and sharper highlights coming in. As a more specific example, here is kind of a dawn scene for some planet, say, and the light's kind of almost on the other side of us here, with using the plain diffuse law, and with a more specular law, you get this more sharp, dramatic daylight thing, which is more or less what happens.
Do you get that with Fong's model?
You don't get it at all with Fong's model.
Oh, you don't?
Right. This is the Torrance-Sparrow model, and that's the Fong model.
Oh, I see.
Are the seeming bands of color there?
That's just, the bands of color are just the resolution of the display, intensity quantization.
Okay.
Yeah.
Say what H is again? I don't have a good feel for what that is.
H is the direction that, if we're assuming a mirror, that's the direction that the normal vector of that mirror had to be in order for the light to bounce off of it and see us. It's the vector that's halfway in between the eye and the light source.
Okay.
So that L dot H and E dot H are both equal. Same angle between E and H and L and H.
It doesn't seem that any of these models take into consideration that when you have, for example, a red surface and a white face that is near that surface, that the light reflected off the red surface tends to make the white surface a little reddish.
The things that I've been talking about today are purely single light source reflection models off of a specific surface. And so it assumes that there's just a point light source of white light coming in and hitting the surface. So we're just kind of getting started in the light reflection game. There's more elaboration than you care to deal with when you start getting into several objects, you know, and multiple reflections and so forth, certainly, yeah.
So how much harder is the Torrance and Sparrow model to calculate than Fong's model?
It's a little harder. It's got the D, G, and F terms all have to be calculated. And it's hard to come up with a measure, but it's maybe, you know, 2 or 3 times as expensive, something like that. The
There's no, yeah.
I've got the exact equations down here. It's basically you ultimately wind up taking the dot product of kind of all the possible combinations of vectors, and those are the numbers that you're plugging in. And it's just a fairly simple 2 or 3 multiplies of each of those things, but dot products themselves are not tremendously cheap if you have to do it once per pixel. Okay, that should be it for today. Anybody have any questions or other problems? Hang around and I'll talk to you after class.